NASA is building a nuclear-powered drone the size of a car, and in 2028, it is going to launch toward a moon where it rains gasoline, rivers flow with liquid natural gas, and the ground is made of frozen organic material that looks like sand but chemically has more in common with crude oil. The mission is called Dragonfly, and it is heading to Titan, Saturn's largest moon, and by a significant margin, the strangest world in our solar system. At minus 179 degrees Celsius, Titan is so cold that water is as hard as granite. And yet its atmosphere is thicker than ours, its surface has dunes, river deltas, and lake shorelines that look strikingly familiar, except none of them contain water, not a drop. And here is the part that keeps planetary scientists awake at night. Titan's chemistry today may be almost identical to the chemistry of early Earth, before life existed. Which means that by flying a nuclear drone across its surface, NASA may be about to watch a 4-billion-year-old experiment play out in real time. To understand why Dragonfly matters, you need to understand what Titan actually is. Because on paper, it sounds like a frozen hellscape. And in some ways it is. But look closer, and it becomes one of the most unsettling places in the solar system. Unsettling not because it is alien, but because it is familiar in exactly the wrong ways. Titan is the second largest moon in the solar system, roughly the size of the planet Mercury. It has a thick nitrogen atmosphere, the same dominant gas as Earth's, with a surface pressure about 50% higher than what you feel standing at sea level on our planet. That is dense enough that if you were standing on Titan's surface, you could strap wings to your arms and fly under your own power. The gravity is low, the air is thick, and the conditions genuinely favor flight in a way that no other world in the solar system does. That fact alone is one of the key reasons NASA chose to send a flying drone rather than a rover. But the real reason Titan matters is its chemistry. The moon's surface is covered in organic compounds, carbon-based molecules that are the basic raw materials from which life is built. Not traces of them, not hints. Titan is soaked in them. Its sand dunes are not silicate rock like Earth's deserts. They are made of frozen hydrocarbon particles. Its rivers carved those channels not with water, but with liquid methane and ethane, the same compounds we burn as natural gas here on Earth. Its seas, some of which are larger than the Caspian Sea, are filled with liquid methane sitting at a temperature of around minus 179 degrees Celsius. And here is the detail that makes planetary scientists genuinely excited in a way that is hard to overstate. The organic chemistry happening in Titan's atmosphere and on its surface is not simple. It is extraordinarily complex. Sunlight and cosmic rays break apart the nitrogen and methane in the upper atmosphere, and those fragments recombine into larger and larger organic molecules that drift down like a slow orange rain, coating everything in a thick layer of complex carbon chemistry. Scientists have identified hundreds of organic compounds in Titan's atmosphere already. And the question that Dragonfly is being sent to answer is this: how far has that chemistry gone? Has it gone all the way to the building blocks of life? Amino acids, nucleotides? Before Dragonfly, humanity has visited Titan exactly once. In 2004, NASA's Cassini spacecraft arrived at Saturn after a 7-year journey. Attached to its underside was a European probe called Huygens, about the size of a large washing machine. On January 14, 2005, Huygens separated from Cassini and began falling toward Titan's surface. What followed was 2 hours and 27 minutes of controlled descent through an alien atmosphere, with a team of scientists in Darmstadt, Germany, sitting and waiting for data that was taking 45 minutes just to travel from Saturn to Earth at the speed of light. Nobody knew what they would find at the surface. Titan's thick orange haze had kept its surface completely hidden from every telescope ever pointed at it. Some scientists thought Huygens might splash down into a global methane ocean. Others thought it might hit solid rock and shatter. there were genuine concerns that the probe might sink into a tar-like sludge before it could transmit anything useful. The uncertainty was total. Every model was a guess. What Huygens actually found was extraordinary. As it descended, its cameras revealed drainage channels carved by liquid methane flowing down from highlands into flatlands. Like river systems, but on a world with no water. It passed through methane clouds. It measured winds shifting direction at different altitudes. And when it finally touched the surface, it landed with a gentle thud on what turned out to be a dry riverbed. Rounded, icy pebbles scattered across a flat plain, shaped by flowing liquid just like the riverbeds on Earth, but made of water ice instead of rock, and shaped by methane instead of water. Huygens transmitted data for 72 minutes after landing. Then Cassini dipped below the horizon, and the signal was lost forever. That 72 minutes was everything we had, our entire direct experience of Titan's surface. For 20 years since, scientists have been studying those 72 minutes of data and coming back with more questions than answers. Dragonfly is the answer to 20 years of questions. Here is the engineering problem. How do you build a drone that can function on a moon 1.5 billion kilometers from Earth in an atmosphere made of nitrogen and methane at temperatures where most materials become brittle, where the sun is so dim it provides barely 1% of the light it gives us on Earth, and where a radio signal takes anywhere from 68 to 84 minutes to travel one way? The answer NASA arrived at is one of the most creative pieces of spacecraft engineering in the agency's history. Dragonfly is an octocopter, 8 rotors arranged in 4 counter-rotating pairs, exactly like a consumer drone you might buy online, except it is the size of a car, weighs roughly 450 kilograms, and is powered by a nuclear generator called a multi-mission radioisotope thermoelectric generator. Think of it as a nuclear battery that produces electricity from the natural decay of plutonium-238, the same type of power source that kept Voyager 1 alive as it crossed into interstellar space. On Titan, solar panels simply are not a practical option. The combination of distance from the sun and Titan's thick haze cuts incoming light to a fraction of what any panel could usefully collect. The nuclear generator does something else critical. It produces heat, and on a world where the ambient temperature is minus 179 degrees Celsius, keeping the electronics and instruments warm enough to function is just as challenging as powering them. Dragonfly's systems are housed inside an insulated, warm electronics box, carefully maintained at a temperature that its components can survive. Now here's the part that makes Titan uniquely suited for this approach. On Earth or Mars, flying a drone is fuel-intensive and covers relatively short distances. But Titan's atmosphere is about 4 times denser than Earth's at sea level, while its gravity is only about 1/7 of Earth's. That combination is extraordinarily favorable for flight. The same rotors that would struggle to lift a heavy payload here become dramatically more effective on Titan. Dragonfly can hop between locations separated by dozens of kilometers in a single flight, something that would take a rover years to accomplish on the ground, if it could do it at all. Over its planned mission of more than 3 years, Dragonfly will cover more than 175 kilometers of Titan's surface, visiting scientifically distinct locations that no single landing site could capture. Dragonfly's first landing site has already been chosen. It is called Shangri-La, a region of dark, organic-rich sand dunes near Titan's equator that scientists believe is one of the best places on the moon to find complex prebiotic chemistry. The name comes from James Hilton's fictional paradise in the Himalayas, and the comparison is not entirely ironic. Shangri-La on Titan is a place where extraordinary chemistry has been accumulating, undisturbed, for billions of years. From there, Dragonfly will make a series of flights, each covering between 8 and 16 kilometers, landing at new sites to sample the surface and measure its composition. Each flight is planned to happen roughly once per Titan day, and one Titan day lasts about 16 Earth days, because Titan is tidally locked to Saturn and rotates very slowly. Between flights, Dragonfly will sit on the surface, recharging its batteries from the nuclear generator, running its science instruments, and transmitting data back to Earth. The most significant destination on Dragonfly's flight plan is Selk Crater, an impact crater roughly 80 kilometers across that scientists believe is one of the most scientifically valuable sites on Titan. When a large meteorite strikes Titan, the impact generates enormous heat in a world that is otherwise permanently frozen. That heat melts the local water ice. Liquid water, even briefly, in contact with Titan's abundant organic chemistry, creates exactly the conditions that scientists believe existed on early Earth before life emerged. The water refreezes within perhaps a few thousand years, but the chemistry it catalyzed may persist essentially indefinitely in Titan's cold, stable environment. Selk Crater is, in other words, a preserved record of what happens when water briefly meets complex organics at -179 degrees Celsius. If the building blocks of life form spontaneously wherever the right ingredients come together, the answer to that question may be frozen into the floor of Selk Crater, exactly where Dragonfly is headed. Dragonfly launches in July 2028 aboard a SpaceX Falcon Heavy from Kennedy Space Center. But just as Parker Solar Probe could not fly directly to the Sun, Dragonfly cannot take a direct route to Saturn. Instead, it will use a series of gravity assists, harnessing the motion and gravity of planets to reshape its trajectory and gain speed. The journey will take nearly 7 years, with arrival at Titan expected in late 2034. When it arrives, Dragonfly will enter Titan's atmosphere inside a protective aeroshell before deploying parachutes to slow its descent. Unlike Huygens, which could only descend and land once, Dragonfly will then power up its rotors and fly to its first landing site. After touchdown, it will capture panoramic images, measure local weather conditions, and analyze the atmosphere with its mass spectrometer. The first data sent back across 1.5 billion kilometers of space will provide humanity's first direct measurements of Titan's surface chemistry since Huygens fell silent in 2005. What those measurements reveal could fundamentally reshape our understanding of how life begins. Here is the part of the story that is often overlooked. Dragonfly is not going to Titan to search for life. It is going to investigate the chemistry that comes before life. On Earth, we have only one example of life emerging from non-living chemistry. From that single case, we cannot tell whether life is an inevitable outcome under the right conditions or an extraordinarily rare accident. Titan offers a chance to observe a second natural experiment under very different conditions, but with some of the same ingredients. If Dragonfly discovers complex organic molecules at Selk Crater, compounds such as amino acids, nucleobases, or other potential building blocks of life, it would suggest that prebiotic chemistry develops naturally wherever the necessary ingredients briefly come together. That would imply that similar processes may be occurring on countless worlds across the universe. If it finds only simpler organic compounds, the message is different. The process exists, but requires conditions Titan cannot fully provide. That result would still be enormously valuable. And if Dragonfly uncovers an unfamiliar form of chemistry that does not resemble anything seen on Earth, it could reveal entirely new pathways toward complexity, perhaps the most intriguing outcome of all. Dragonfly costs $3.35 billion. It will take 7 years to get where it is going, spend more than 3 years exploring once it arrives, and return science data that will take decades for researchers to fully analyze. It is, by any measure, one of the most ambitious planetary science missions ever funded by any space agency on Earth, and it is worth every penny of it. Because the question it is going to Titan to answer, does the chemistry of life arise naturally wherever the conditions allow, is not just a scientific question. It is the question. Every other question about whether we are alone in the universe, about whether life is a cosmic accident or a cosmic inevitability, about what the long-term future of intelligence in this galaxy looks like, hangs on the answer. Right now, assembly and testing is actively underway at the Johns Hopkins Applied Physics Laboratory in Maryland. The hardware is being built. The instruments are being calibrated. The launch window in July 2028 is less than 2 years away. Humanity is, at this very moment, constructing a machine that will fly through the skies of another world and tell us something about our own origins that we have never been able to know before. Titan has been sitting there for 4.5 billion years, preserving its chemistry in the cold and the dark, waiting. In 2034, we are finally going to go look. On January 14, 2005, a probe the size of a washing machine survived a 2.5-hour descent through an alien atmosphere and landed on a frozen riverbed 1.5 billion kilometers from Earth. It had just 72 minutes to tell us what it found before the signal was lost forever. Nearly 30 years later, humanity is going back. Dragonfly will not simply land on Titan. It will fly across its surface, explore multiple locations, and operate for years on a world where sunlight is little more than a distant glow. Dragonfly is more than a mission. It is part of humanity's attempt to answer one of its oldest questions. Are we alone? Or is life a natural consequence of the universe's chemistry? The universe may already hold the answer. In 2034, we will finally be close enough to start listening. If you enjoyed this video, a like genuinely helps the channel reach more people interested in space and science. And if you want to follow the story of Dragonfly all the way to Titan, consider subscribing.